So last week I talked about the category of dendroidal sets, which is an extension of the category of simplicial sets. So there is an embedding here, and it relates to operads in exactly the same way as categories relate to simplicial sets. And we can, for example, use it via nerve functor, and here there's an inclusion too, because remember that operads means colored operads, and if a colored operad has unary operations only, it is exactly the same as a category. So there's an embedding here which hopefully denotes J shriek. And much of the craftsmanship of dealing with dendroidal sets is sort of a mixture of simplicial techniques and trying to deal with all these automorphism groups of trees, which can get in the way quite a bit.
Excuse me. Why didn't the bar on left? Category. Category.
The category of small categories. Sorry, I didn't hear your question. So today, my plan for today, my ideal plan for today would have been to talk a bit about homotopy theory. Homotopy theory, it's not easy close to the board. Then to talk about the homotopy theory of dendroidal sets. And then talk about Lurie's homotopy theory of infinity-operads. Okay. So my guess is that I will only get to here before you're all worn out, and so we'll have to see what we do about this. Maybe we'll find another occasion to talk about the rest, but we'll see how it goes. I could also talk only about the second and third part if everybody knows everything about Quillen model categories, but I think this is perhaps unwise because you've been referring to them implicitly also quite a bit. So I will begin with so this will be A, B, C. So A will be a review of Quillen model categories. And this goes back to Quillen's paper on rational homotopy theory of the late 60s. And there Quillen gave various models for rational homotopy theory. So you want to study simply connected topological spaces, and you call two of them the same, equivalent if they have the same rational homology, and you try to model the category that you get. And you can do this using certain kinds of co-commutative co-algebras or differential-graded Lie algebras. And what does it mean? What does modeling a space by a differential-graded Lie algebra mean? Okay. So he gave a very precise formalism for this, which is now sort of common language among topologists and extremely effective. So I would like to take 20 minutes or so to remind you of that language. So we start with the category E, the category of espace, and so a Quillen model structure. Quillen model structure on E is given by three classes of maps. the vibrations, co-vibrations, and the weak equivalences and they should satisfy some axioms. 5 axioms. So these axioms are from the paper of Quillen that I mentioned. There are various refinements of the axioms or modifications or slight strengthenings, which I maybe will mention as we go along. So the first axiom has nothing to do with these 3 classes of maps, but only with the category E, and it just says that finite limits and co-limits. The second axiom says that if you have 2 composable arrows in E, then and their composition, you have 3 arrows, and then if 2 of them are weak equivalences, then so is the third. So for a composition G composed with F of arrows F and G and E, if 2 of these are weak equivalences, then so is the third. So that's an axiom that only refers to the class of weak equivalences. And the idea is to be able to construct what is called the homotopy category of E. That's the category you get by inverting these weak equivalences. They're not isomorphisms, but you want to turn them into isomorphisms. So this is quite a natural axiom if you think of, because if you turn two out of F, G, and G composed with F into isomorphisms, then of course you have to turn the third into an isomorphism as well. CM3 says that each of the 3 classes are closed on the retract. So this is referring to the notion of one arrow being a retract of another arrow. Okay, so an arrow F is a retract of an arrow G. Let's say this one goes from A to B, this one goes from X to Y. If and only if A is a retract of X, and B is a retract of Y, in such a way that it is compatible with these maps F and G. Okay? And everything commutes. So these are axioms which in the examples are often very easy to verify. And the next 2 examples are next 2 axioms are a bit more complicated.
Are you monomorphism?
The arrows R and I establish exhibit A as a retract of X. Okay, so R composed with I is the identity. Yeah, so I has to be a monomorphism.
No, but
Pardon?
because you did not put it
I put.
for I not for G.
I see. Yes, I'm not very.
Was
Yes.
on purpose or not?
No, there was no deeper meaning here. No. Thank you. CM4 is what is called the lifting axiom. In a square, commutative square, when I draw a diagram, it will be a commutative diagram unless I specifically comment that it might not be. A, B, U, Y, X, P, F, G. Where U is a cofibration and P is a vibration. you can find a diagonal which makes both triangles commute. A diagonal, a lift, diagonal H, making both triangles commute, exists as soon as one of U and P is a weak equivalence. So this axiom is at the same time, it talks about some sort of homotopy lifting. You can lift G to H, and homotopy extension. You can extend F along this cofibration to an H. A diagonal H making both triangles commute exists as soon as one of U and P is a weak equivalence. The chalk is perhaps not improving my handwriting. You can blame it on the chalk. Theorem 5. Every map x to y can be factored as a cofibration followed by a fibration so let's write it x u z p y in two ways. One in which U is also a weak equivalence, and one in which P is also. And maybe a bit of terminology. So a map, which is both a fibration and a weak equivalence, well, it's called a trivial fibration. And the same for the cofibrations. Okay? So you can factor a map as a trivial cofibration followed by a fibration, or as a cofibration followed by a trivial fibration. You can find the lifting if U is a trivial cofibration and P is a fibration, or if U is a cofibration and P is a trivial fibration. Right. So in particular, the map 0 to y, let's say, 0 is the initial object, which is the empty colimit, so it exists, can be self-factored. Cofibration, trivial fibration. And an object with the property that the map from the initial object is a cofibration is called a cofibrant object. Okay? So this is a cofibrant object. And this is called a cofibrant resolution of y. So we've seen some examples of this. I will mention examples later, but some examples have come along in the past few weeks in the case of associative algebras and operads. So every object is weakly equivalent to a cofibrant object. Yeah?
What did you write over the arrow? Why into y? Trivial.
Trivial vibration. I'll have to write it more clearly. And similarly and dually, x to 1, the terminal object, can be factored as x trivial cofibration x sub f vibration to 1. And an object with the property that the map to the terminal object is a vibration is called a vibrant object. And so xf, this is called a vibrant resolution of x. Okay. So you see that if you turn the weak equivalences into isomorphisms, then every object is isomorphic to a cofibrant object, and every object is isomorphic to a vibrant object, and if you do both, then every object becomes isomorphic to an object which is vibrant as well as cofibrant. Yeah? So the homotopy category, or maybe one other thing. One other such factorization. Also, the codiagonal x plus x to x. So that's the sum of two copies of x, which exists again by the finite coproducts, can be factored as a trivial vibration preceded by a cofibration. Now I'm not sure what, okay, let me call this cyl of x, the cylinder on x. You could also denote it I tensor x, even if you don't have an I and you don't have a tensor, okay? But you should think of it as a space which parameterizes homotopies between maps from X. Okay, a cylinder for X. Okay. So then we can construct the homotopy category Ho of E, which is by definition E with the weak equivalences universally turned into isomorphisms. So you formally add inverses to an inverse to every weak equivalence, and then you generate a category. Can be described explicitly by objects those X and E which are both vibrant and cofibrant, and arrows from X to Y are homotopy classes of maps from X to Y in E, maps in E, where homotopy is defined by as okay, so here you have x plus x, here is this cofibration from x plus x, which is still on the board, and here you have the two maps f and g. I don't know how to denote this, f comma g maybe. Where homotopy between f and g okay. And slightly more generally, one more remark about this general setup. Maybe I'll try to squeeze it in here on the left. So more generally, if X is cofibrant and Y is fibrant, then arrows X to Y in HO-E can be described, or are, maybe I should have said, as such homotopy classes. So this is a bit of pure category theory, and once you see the axioms and you have the description, you can go home and prove this, I think. It's not completely trivial, but it's doable. Okay, so what maybe for us, so let's look at some examples. Well, the whole lecture, in some sense, will be about examples relating to operads and dendroidal sets. So I shouldn't dwell too long on examples of different kinds, but maybe at least historically, examples. Some of the basic examples, and I will not write everything down, I think, but topological spaces. Simplicial sets, chain complexes, or cochain complexes, categories, simplicial groups, maybe. I mean, the list is infinite. Differential graded Lie algebras, and so on. Okay. Ad infinitum. Operads, maybe. Well. Sorry?
No, you can carry on there for examples.
Yes. So, but let's just look a little bit at the first couple of examples. Topological spaces. Okay. The fibrations here are proving the axioms is difficult for topological spaces, and it sort of captures all the basic business of homotopy theory. The fibrations are the self fibrations. The cofibrations are given by extending a space by cells, so relative CW complexes. The weak equivalences are the maps which induce isomorphisms in homotopy groups. Yeah? And hidden inside this theorem, this description of how of E is the Whitehead theorem. That if you have a map between CW complexes which induces isomorphism in homotopy groups, then it has a homotopy inverse. So I emphasize this point to illustrate that knowing that it's often very hard to prove that these axioms are true in a given example, but conversely you get a lot out of it. The dual of this statement is also true. So for categories, or for groupoids, maybe even simpler, this also has a model structure where the weak equivalences are the equivalences of categories, the cofibrations are the functors which are injective on objects, and the fibrations are not exactly like the Grothendieck fibrations, but are the functors for which you can lift an isomorphism, some sort of path lifting property. This is trivial to check, you can go home and check it, but as a consequence you get very little out of it, okay? You cannot prove much about categories that you didn't know, now that you know it's a model structure. Simplicial sets is the next very classical example, which was intensively used by Quillen. So here the weak equivalences are defined by geometric realization. The fibrations are the cone fibrations, and the cofibrations are just the monomorphisms. So there are lots of cofibrations, all the objects are cofibrant, but it's not so easy to be a fibration. It's not so easy to be a fibrant object. It has to be a Cannes complex, and we talked about Cannes complexes last week. It has to have all kinds of filling conditions. The object has to be complete in some sense. Chain complexes. There are two things you can do. You can, the weak equivalences are the quasi-isomorphisms, the maps inducing isomorphisms in homology, and then you have a choice. You can try to mimic injective resolutions by controlling your fibrations. They have to be surjections with injective kernel. Or you can try to mimic projective resolutions by having the fibrations just as surjections and having the cofibrations to be the monomorphisms with projective co-kernel in each degree. Okay, so there you capture, if establishing the validity of the axioms in these two cases with the same weak equivalences gives you a lot of standard 1960s homological algebra, all the manipulations of projective and injective resolutions. And for example, this description of the homotopy category somehow reflects the fact that if you know that you can extend, how is it? Discussing derived functors, you try to map into injective resolutions, and you know that this is unique up to homotopy. Yeah? So that fact is hidden in this theorem as well. Okay. So now the next. So that's my first half of the 20-minute review of Quillen model categories. Okay, so the next question is, how do you compare different such categories? Yeah? So this was the main goal in this original Quillen paper, and there are already some examples here. For example, we know that topological simplicial sets model topological spaces. Yeah? And every space can be approximated by a CW complex, and one way to do that is by taking the geometric realization of a simplicial set. So for this, there is a notion of a good map between model categories. So to comparing such model categories is done via what are called Quillen pairs. So So if you have two model categories, E and D, so these are categories equipped with, each of them equipped with 3 classes of maps, satisfying the axioms, but I'm just writing E and D, although I should have written maybe E and these 3 classes.
Just a question.
Yes?
Weak equivalence, is it automatically a fibration and cofibration?
No.
No.
No. So there is a pair of adjoint functors, which for various reasons I'm inclined to denote like this. It's adjoint pair. Left adjoint on the left and on top. So maybe I should have written it like this. On the left and on top. To emphasize this just once. And with the following properties, such that F shriek preserves cofibrations and trivial cofibrations. And now you can do a bit of simple category theory and use these lifting properties for the squares and play with that and the adjunctions, and you can easily translate this into a dual condition on F upper star. So let me write it all. F upper star preserves fibrations and trivial fibrations. Okay, I should maybe have said trivial fibrations and fibrations. F shriek preserving cofibrations is the same as F upper star preserving trivial fibrations, and F upper star preserving fibrations is the same as F shriek preserving trivial cofibrations. Okay, and that's very easily seen with this commutative square.
Maybe I
Question?
The definition of a trivial cofibration or fibration, what it is. I missed it.
Yes, so I call a map trivial if it is also a weak equivalence.
Oh, okay.
So a trivial fibration is a map which is both a fibration and a weak
Oh,
equivalence.
okay.
And the same for cofibration.
That answers my previous question.
Yes. Okay, so one of the important consequences of these conditions is that it follows that F shriek and F upper star induce adjoint functors Ho E, Ho D. And they're called the left derived of F shriek and the right derived of F upper star. So maybe let's stare a little bit at this. So, there are 2 ways of viewing Ho of E. One way is to take the same objects as E and to invert the weak equivalences, supposing you can do this. Okay? Then, of course, F shriek sends an object of E to an object of D, but you cannot prove that this cannot be made into a functor. Yeah? What you have to do is first replace the object by a cofibrant object and then apply F shriek. On the other viewpoint, this has as object fibrant and cofibrant objects. So you don't need to do anything. Okay? You can just apply F shriek. But F shriek of something is not cofibrant and fibrant. So then on the other side you would have to make it will be cofibrant, but you would have to make it fibrant to land in Ho D viewed with fibrant and cofibrant objects only. So there's always something to derive, so to say. Okay. And if this last adjoint pair is an equivalence of categories, then we call the original pair F shriek and F upper star a Quillen equivalence. And of course you can rephrase this directly in terms of F shriek and F upper star. You just calculate what the unit and co-unit of here should be and ask these to be weak equivalences. Yeah. So let me do on a piece of scratch paper where I will erase it immediately. So you start with an object E, which is cofibrant. You apply F shriek of E, which will be cofibrant but not fibrant. You take what is called a fibrant resolution, which I denoted sub F. That's a bit unfortunate. So this is a trivial cofibration, and this is fibrant. And then you apply F upper star to that. And of course, you will get a map F upper star, F shriek E by applying F upper star to this trivial cofibration. You don't know what happens to it, but you get this map. And then you have the original co-unit, which sits here. And you take the composition, and that's the derived co-unit. Co-unit. And that should be a weak equivalence for every cofibrant object E. Okay? And there is a dual condition for the... Why do I say co-unit if I want to say unit? Because I was thinking there is a dual condition for the co-unit. Yeah? So when one says that, where is my list? That simplicial sets and topological spaces model the same homotopy theory, one way to make that precise is to establish a Quillen equivalence between spaces and simplicial sets, and this is indeed the case. Geometric realization and singular complex are such a Quillen equivalence. Okay? And when you say that differential graded Lie algebras with some connectivity assumptions over the rationals model rational homotopy types, you establish a Quillen equivalence between the model category of differential graded Lie algebras and the model category of topological spaces with rational equivalences. Now, from this example, you cannot compose Quillen equivalences because they have a specific, you want to view them as equivalences, but they have a specific direction. Okay, so when you say that two model categories are Quillen equivalent, it can also mean that there is a zigzag of Quillen equivalences between them. Okay. So maybe that will do for, that will have to do for a little introduction to homotopy theory. But anyway, I think one has to know this language these days. Sorry to say.
And you say that get intuition, we work with a chain complex, it's the best way to
That's a very good example to keep some intuition. Okay, and the derived category. So then the homotopy category is the usual derived category. Where you know that you have to take injective complexes only, for example. Yeah. And if you do that, every object is cofibrant, so it is exactly restricting yourself to cofibrant and fibrant objects. So another example. is the category of operads of uncolored, let's say classical operads. Sorry, I'm a bit in the dark. Colored operads in chain complexes or simplicial sets or topological spaces.
It's not true for colored operads?
Yes, it is true for colored operads also, but I will get to it.
Okay.
Because then the situation becomes a bit more complicated.
It's
Uh,
more complicated for colored operads.
Well, I will make a remark about
Okay,
this.
fine.
So first of all, let's fix an ambient category. For example, simplicial sets. Okay? Then you can look at an operad. So a simplicial operad is given by simplicial sets P of n, simplicial operad P. Okay? And we call P to Q a vibration or weak equivalence if and only if each Pn to Qn is one of simplicial sets. Okay. And this defines the model structure. And if you don't like simplicial sets, but you'd rather go to chain complexes like Bruno, then then you can write exactly the same sentence by replacing simplicial sets with chain complexes, and you get the model structure again. Okay. And I haven't told you what the cofibrations are, or the cofibrant operads, but these are these resolutions that we talked about. For example, cobar-bar of last week, or Boatman-Folk of 3 weeks ago. So if you, so exactly the same thing to go into John's question a little bit, exactly the same is true for operads, colored operads with a fixed set of colors C. Okay. You just say for each n+1 tuple of colors, P C1 up to Cn C, you say that P, I will just write it once but then erase it. You say that this is a weak equivalence instead of just this. Yeah. Okay. So it gets a little harder if you want to study the category of colored operads where you allow the colors to change. Yeah. And so I will begin by discussing a simple.
Can I ask it?
Yes.
You said what you do in an example, but now suppose you think about how you would say the category of operads in a symmetric monoidal category was a closed model category. Can you tell what the axioms on the target category have to be?
Yes.
I mean, you wrote a paper about that.
Yes. So I can tell you, but let's not go into this detailed description of this now. But you emphasize an important point, namely, we can talk about operads in chain complexes or simplicial sets or topological spaces because these are monoidal categories. Yeah? And we have the theorem that these are model structures. These are model categories. These satisfy the equivalent axioms on the basis of this definition, because the model structure on these three target categories, chain complexes, simplicial sets, and topological spaces, is compatible with a tensor product in some sense. And there's also a notion for this. It's called a monoidal model category. It's a category which is both equivalent model category and a monoidal or a tensor category, and there is some compatibility between the two. Okay. Good. So let's go. Let's go back to maybe the simplest example. Now, let me write down the square that I started with. Simplicial sets, dendroidal sets, operads, and categories. And now I will write all the functors. So this is the nerve, and this is the left adjoint to the nerve, and this is I shriek, which is just the inclusion, and this is I upper star. I upper star takes, in some sense, the simplicial core of a dendroidal set. Its linear part. Here we have this inclusion, J shriek, and of course, if you have a colored operad, you can ignore all the operations except for the unary ones, and this gives you a category. Some people call it the underlying category of the operad. And there is a nerve here and a toe here. Okay. So let's stare at this square a little bit. So I've told you, for two of these, I've told you that they're model categories. Okay? And namely, the category of small categories and the category of simplicial sets. So cat, I will be more explicit. Cat carries a model structure Cofibrations are the functors which are 1, 1 on objects. Weak equivalences are equivalences of categories. And fibrations have lifting property with respect to isomorphisms. So let me be a bit more specific. If you have a category D and a functor to C, and you have an isomorphism in C, C primed, and you have an object over C, D, so P of D is C, then you can lift the isomorphism to an isomorphism here to some object D primed which maps to C primed. Okay? So it's exactly like path lifting, where a path is an isomorphism. Okay. So simplicial sets carries the classical Kant-Quillen model structure. But this pair of functors is not a Quillen pair. It's not a Quillen square. This is called a spoonerism, I think. A Quillen pair for these two model structures. Because the nerve of a category is a Kant complex only if the category is a groupoid. Okay? So to make this a Quillen pair, you can do two things. There is one very easy thing. You can replace the category of categories by the category of groupoids. But of course you throw away a lot of stuff. Or you change the model structure on simplicial sets. Okay? So there is a model structure on simplicial sets with fewer weak equivalences. It's called the Joyal model structure. So tau and n is a Quillen pair not for the Can-Quillen structure, but for the Joyal structure of simplicial sets. And this Joyal structure is very closely related to things which I discussed last week. Namely, whereas the fibrant objects in the Can-Quillen structure are the Kant complexes, the fibrant objects in this Joyal structure are the what are called inner Kant complexes or weak Kant complexes or infinity categories. Yeah? So the fibrant objects are infinity categories. So if you want to know more about infinity categories, you can read the 2,000 pages of Lurie, which gives an exhaustive treatment of the subject.
Should we really think the nerves of infinity categories?
Or is this the definition of infinity category?
So the nerve of a category will be a special case of an infinity category. Infinity category is a little like a category up to homotopy. And among those, there are the strict categories, and these come from the nerve. But these are not all the fibrant objects are hit by the nerve.
But I mean,
do I misunderstand your question?
yeah, no, I think you've answered the question I ought to have asked.
Sorry, can I? So what do you have to change on simplicial set? You take another weak, strictly weak
I
equivalence?
take fewer weak equivalences.
Fewer weak equivalences.
Fewer weak equivalences.
Exactly.
I keep the cofibrations the same. These are still the
And then you think,
monomorphisms.
yes,
So I have fewer trivial cofibrations, and because of this I have more fibrations, because these are dual in some sense. So it's easier to be a fibrant object.
It's exactly the same phenomenon than between de Gili algebras and co-commutative coalgebras. The quasi-ISO are preserved under the Cobalt form term when we have inequivalent because of connectivity. If we drop the connectivity assumption, we have to take fewer weak equivalences.
In fact, there is a whole gymnastics about this too. If you have a Quillen model category, but it should satisfy a few more axioms. It should be cofibrantly generated.
Yes.
For example, all these examples are cofibrantly generated. You can always keep the same class of cofibrations, add a few designated arrows that you want to be weak equivalences, so you invert a little bit more, and then get a new model structure with fewer fibrant objects. And that's called left bow-fluid localization.
And these two model categories are related by this.
Exactly. So Can-Quillen is a left bow-fluid localization of Joyal.
Exactly.
But of course, Joyal came 50 years up. Well, how long? 40 years after Can-Quillen, right? So in hindsight,
So tomorrow I will go back to this for infinity algebras. We need that too.
very good. So maybe I will write down the theorem, or maybe two, and then we'll take a break. So the first, proposition, observation maybe. There is a model structure on operads, colored operads, like the one on the cat, where a map P to Q is a weak equivalence if and only if it is fully faithful which means that P of, let's call this F, C1, Cn, C to Q of FC1, FCn, FC is an isomorphism for all colors C1, Cn, C of P. This map, I didn't denote this here, but last week I said this map is really a pair of maps, one on the colors and one on the operation, so I call the one on the colors also F. Okay? And it is essentially surjective. Yeah. But you know that the equivalence of categories is one which is fully faithful and essentially surjective, so I'm going to put these two in one condition. J upper star of P to J upper star of Q is an equivalence of categories. Because this suits me well when I want to make a more general statement later. Okay?
So you're saying that this last line is the same as the line above? It's equivalent to the line above?
No.
No.
But there is considerable overlap.
Yeah.
Okay? This is, I'm saying that, so for the unary operations, I get an equivalence of categories. So every color of Q is isomorphic to the image of a color of P. That's saying that this is essentially surjective.
Yeah.
And this one has to be fully faithful, but that's already contained in this statement for n equals 1.
Yeah.
Okay? Okay. And the fibrations, you can check the fibrations are exactly the same as for categories, and you can easily see that this is an equivalent pair. Yeah? This makes, if I take a piece of, okay, this makes J shriek, J upper star into equivalent pair.
Is this comparison cat and opera, you say it's set opera?
Set for the moment. Later, after the break, there will be a statement like this for simplicial categories and simplicial operads, which is more than an observation because you really have to work them. Because we don't have isomorphisms anymore here. These are simplicial sets, and it's just a weak homotopy equivalence. But that will come after the break.
So you said that between ordinary categories and ordinary operas, set operas,
Yeah.
there is equivalent.
Yeah.
The obvious factor from equivalent.
Okay, and then the theorem, which I approved with Denis Charles-Szynski, is that there is a model structure, there is a equivalent model structure for Dendroidal sets, for which the cofibrations are the normal monomorphisms, which I defined last week. So I remind you, a map is a normal monomorphism if the automorphism groups of trees act freely on the complement of the image of the monomorphism. So it's like adding free cells. And the fibrant objects are precisely the infinity-operads. So I also remind you that a map X is an infinity-operad if whenever you have a map from a horn of a tree, this is the boundary of the tree, except the face contracting an inner edge E, you can always extend it to the tree. Okay. Infinity-operad or dendroidal inner Kant complex. Now you may start protesting because I'm only giving you the cofibrations and the fibrant objects. But the cofibrations and the fibrant objects determine the entire model structure. Yeah? This is not to say that if you have cofibrations and fibrant object that you have a model structure. But if you have a model structure, it's uniquely determined by the cofibrations and the fibrant objects. Okay. B. If you have a model structure on any category and you take a comma category or a localization or a slice category, with the same classes of maps, it again satisfies the actions for the Quillen model category. So there is an induced model structure on dendroidal sets over this object eta, which was the unit of the monoidal structure. And this is precisely the Joyal model structure. Wait a minute. How was this again? Well, I said last week, this category dendroidal sets over eta is actually isomorphic to the category of simplicial sets. Yeah? Under the isomorphism, or modulo the isomorphism, dendroidal sets over eta equals simplicial sets. Okay, maybe I'll put this here, and I shriek, I upper star from a Quillen pair. Not a Quillen equivalence, of course, because there are a lot more operads than categories, and there are a lot more simplicial sets than, a lot more dendroidal sets than simplicial sets. Okay, and for this model structure, the right-hand nerve is also part of a Quillen pair. Okay, this one here. So let me put that up as part C. This makes dendroidal sets, tau, and operads into a Quillen pair. No. So what I will discuss after the break, and which is perhaps what you have in mind, is that if I jazz up this category to be simplicial operads, it becomes something like this, becomes a Quillen equivalence. So dendroidal sets form a small combinatorial model for simplicial or topological operads. Okay? And the equivalence read in the other direction says that any infinity-operad can be strictified to a real operad at the cost of introducing a topology. But let's not do everything at once. So I didn't tell you what the weak equivalences are, but after the break, maybe the first thing I will do is the weak equivalences between fibrant objects can be described explicitly as okay, so let's take a 5-minute break. Well, I'm keeping myself on the hook because otherwise I should have turned off the microphone before saying this.